recording. All right, so this is the just a Tuesday night before the test, so you guys can go ahead and start asking questions.
Okay, I guess I'll go first. I had a question. I was going over the PowerPoint slideshow you put together that says more review. And I was on slide 12 where the two balls collide at different angles.
Okay.
And I was wondering if you could walk through. I kind of set up the equation for the coefficient of restitution already, but when I get to doing the impulse momentum equation, I was wondering when we use the angles to apply to it.
Is it this problem right here?
Yes, it is.
Okay. Yeah, so what you want to do for these types of things, these are those oblique central impacts. And remember, as we're doing these, that big, do you remember what the big assumption is for these when we're using E?
No, I don't.
Anybody else? Mike or Jeff, do you remember?
Isn't it that momentum is conserved in the normal direction?
For most of these cases, if it's two free balls like this, that's exactly correct. But you might also end up saying the one that always holds if there's no force in the tangential direction, right? So kind of like no friction in that tangential direction. So this would be our tangential direction there. Does that make sense?
Yep.
Okay, and then I could do my normal direction here. It would be okay if I decided to make that my positive normal direction too. It's really pretty arbitrary in the end. You get to decide how that goes. Okay, so but let's say we're going to use what I just drew up there. Right, so now kind of how the angles end up coming in is that 50 degrees doesn't matter quite as much, right? It was just kind of showing you where it was from vertical. But now, we end up having, because if we draw out our impulse momentum diagram, say, let's just start it and do it for B, right? Then I've got one that's coming down there in the N direction, and that's going to be like an MB VB initial. And then for these cases, we actually know the direction of the impulsive force, right? So that's going to act right along that N direction there. Okay, and then we get to sort of decide which way we think it's going to go afterwards, right? But really in this case, it's either, because I don't have any initial velocity in the tangential direction, it's either going to bounce right back, right? Or it's going to go keep going sort of in that same direction. Does that make sense to you?
Yeah.
Okay, so then for the second one, and this was for B, right? And then I think where your question's coming in is sort of the trig part of these things. It's always a little bit of a pain. So if I'm going to do my A over here on the left. So I've got, it's coming in at this direction. So that's my MA VA, right? And then I've got some sort of impulse. In which direction is that acting?
Opposite towards B along the line of action.
Right. And do I have any other impulsive forces?
No.
No. Okay. So then that means now afterwards it's going to end up going some other direction, right? And you get to again decide what that's going to be. So, do you have an intuition for which way you think that might go?
Probably maybe down to the somewhere down to the right, maybe.
Yeah, so we don't quite know. So one thing I sometimes do is I'll just guess that it's going in positive directions, right? Because I actually agree with what your intuition is, but sometimes mathematically it's easier to just do it in the plus direction and then see what your answer is and see if that makes sense.
Okay.
Professor?
Right. Yeah.
How did you know that there were no forces acting in the tangential direction?
That's whenever you have an E problem, that's what we were just saying at the beginning is if you have a coefficient of restitution, then that is the primary assumption for those types of problems.
But isn't some of the velocity of A, doesn't that have a tangential component to it?
Yes, but it's not going to impart any force in the tangential direction here. So repeat
Okay.
your question. Maybe I didn't. So the force in the tangent, right? There's no force, impulsive force in the tangential direction for either of these.
Okay.
Okay, and that doesn't happen very often, except for if you have sort of a spherical thing like this, or if you're modeling something like this, like we did with the Boulder homework problem.
Right.
Okay, so
Okay.
there's not a whole lot of cases where you're gonna use this. There are some, like I had students design a soccer playing machine where you actually use this, but most because it went on the front of in front of a wheelchair. So that's just the assumption that you make when you're doing these problems, as you say, okay, there's not going to be very much friction, and that's not too bad if you have two spherical shapes like this, right? So you would not. That's again why I said you would not use this for the car crash types of problems.
Okay.
Okay, so now what we do is we're looking here, what we'll typically do, because that E equation, like Mike, you just said you had set that up already, right, where it's in the n direction. Well, then what we can do is the V of A after the impact in the tangential direction is equal to whatever it was initially.
Mm-hmm.
Okay, and that's because we don't have any impulsive forces in the tangential direction.
Yeah.
So how much of that VA is in the T direction?
That would be 6 sine of 40 degrees.
Okay, so 6 times sine 40 degrees. And look at how we drew it in our plus directions?
It would be in the negative.
Yeah. Okay, so does that make right sense to you so far?
Yeah.
And then how about for VB prime in the T direction?
That'd be 0.
Yeah, because it's got nothing in the beginning, so it's just going to either bounce right back out or it's going to keep going forward.
Okay.
All right. So then, what's another relationship you can use for it?
You could use what did I use? Relationship for what? For what are you asking again? Can you repeat?
Just what else would you use to try to solve the problem?
The equation with E is what I was trying to use to get another equation.
Okay, so if we have our E, and we know that was given, right, is 0.8, I think, right?
Yeah.
So now we just look at what we have after the impact, right? So, and depending, I can't remember how I give it to you, but basically if we do VB prime, and that's going to be in the normal direction, minus VA prime, and that's also, of course, in the normal direction, over VA, so that's initial in the normal, minus VB, and that's in the normal. So is that part okay?
That's good.
Quick question on what you just said.
Uh-huh.
So is when we do coefficient of restitution, are those velocities to be assumed always in the n direction?
Yes.
Okay.
So if I look here, right, then VAN, what is that going to end up being?
That's going to be whatever the negative 6 cosine of 40 degrees.
Okay. Is everybody okay with that? And then how about the VBN?
That'd be negative 4 meters per second.
Yeah. Okay, and then how about the VAN prime?
VAN prime. VA prime T, so would that also be 6 cosine 4? That's where I'm kind of lost.
Right. So
that's where I got to, and I just couldn't go past that.
Yeah. So do we know what that is?
Is that what we're solving for?
That's part of what we're solving for, right? So I don't know what that is.
Okay.
But I know what this one is.
0.
0, yeah. Wait, yeah.
Oh, no.
No, yeah, no, it's not.
Nope, I don't know what that is.
Yeah, yeah,
Okay.
you don't know what it is.
So I've got two unknowns there, right? So
Okay.
it's always
okay.
a good idea keeping track of those things. So so that means I have two unknowns and really only that one relationship, right, that deals with the end. So what other relationship can I now use?
The impulse momentum equation.
Exactly, right? So I can do those separate or I can combine them, because in this case, do I have conservation of linear momentum if I combine the two balls into one system?
Yes.
Right. Okay. So does that make sense to everybody? The questions there?
And how do you know when something has conserved linear momentum?
Somebody else tell me that. What's the answer
Isn't
to
it
that?
usually along the line of impact is usually always linear momentum is conserved?
Well, not necessarily, because I could have, like this, I could have some sort of like if this right here was a rope, right, then I'd have a component of an impulse in the normal direction. So the key is really to look at my impulse momentum diagrams, and that's why I harp on those so much, right? What are other things? What does it mean for us to have conservation of linear momentum?
Doesn't that just mean the R delta T's are in equal and opposite directions?
Yep, that's part. And what else?
And it has no other external force besides that, so we can set those two equations equal to each other, or add them together, have them cancel.
Yeah. So in the end, right, I could have conservation in a certain direction, right? And there are a couple of those examples, right? So Jeff, did you end up calling in on a phone to get the audio?
Yeah. So yeah,
Okay.
I'm on my phone and the computer.
Okay, cool. I'm like I've been saying, I need to actually take a little course on the Zoom because they just switched that over last time, and but that's good that you could get in then without having to go through voice over IP. Okay, so yeah, basically you're just looking at the total external impulses, right? So in this case, those two impulses, the R delta T's, canceled one another out, right? But there is an example problem, like I mentioned in the book, where I think there's like something here and a ball drops down and hits, right? So in this case, you have another impulse due to the rope.
Mm-hmm.
Okay, so that's why it's critical to do these. But in this case, there are two free bodies hitting. So in this case, you definitely have where MA, VAN plus MB, VBN is going to equal MB, VB prime N plus, I guess I should have written that the other way, but it's all right. VA prime N. Can you guys, sorry, the mouse is a little weird at the very end, or my pen. Does everybody understand that?
Yeah.
Yeah.
Okay. So what are my unknowns in this equation?
It would be VB prime and VA prime.
Yeah, right. So, and this is a prime right here. Okay. So this is unknown, that's unknown. So that's your second equation now.
And solve for one and then plug in together.
Yeah, however you want to do it. You can do matrix algebra, you can do linear addition. But now when it asks for the velocity, then remember it combines both this, right, the tangential and the normal directions. Okay, so I'm asking for the velocity. You'd need to figure out what the full component is. Does that make sense to you?
Yeah.
But no matter what, B is only going to have VB prime is only going to have a normal component to it, right?
Right, because initially there was no tangential component.
Okay.
Yeah. Okay, any other questions about this one?
Oh, go ahead.
So if you were talking about a problem in which there would be an external force, how would you deal with that in terms of the equation? Would there just be an extra term in that momentum equation that you have written out there on the right side?
There could be, or what you might have is, let's say in this case, I'm just drawing in some sort of but like if there was some sort of a rope on this one instead, right? I'm sorry, I should have stayed with the B, but let's just say it was on A. Then I would have like a T delta T.
Okay.
So now, is conservation of linear momentum in any direction at all?
No. Is
Did-
there? I'm not sure.
So does this and this still cancel?
Yes.
Yeah. So if I look at my diagrams in the X direction, do I have any other impulse?
No.
No, because the T delta T is just in the vertical direction.
Okay, so you'd have to do it in Cartesian coordinates and not
Yeah.
Okay.
Yeah.
Okay.
Okay, and there's two sample problems in the book that go over that.
Okay.
So we didn't stress that a whole lot, but that doesn't mean there couldn't be one. Maybe another instructor thinks it is more important. So there could potentially be one on the final exam. And I could certainly, I don't know if I would ask you a full-blown problem like that, but I might ask you to set it up or draw the impulse momentum diagram.
Okay.
I had a question. So on the video that you put online, the half-hour video, I was wondering if you have any of those solutions anywhere, because I was working them out and I couldn't find them. Specifically the pinball one. So I set it up and I'm pretty sure I have the process correct, but you had said to double check if it would clear the top. And the only way I could think of doing that was if the velocity at the top was greater than 0, but it was all in terms of variables, so I wasn't really sure how to approach that.
Okay, so let me see.
Do you know which problem I'm talking about?
I think so. I just need to see how I
Okay.
get to it. Let's see if I've...
That one.
Yeah.
Yeah.
Yeah. So on here, how do you have to decide if it gets high enough?
So, well, I'm just going to explain my general process of thought when I was doing this. So what I did was I looked at point D and found the velocity in the x direction through projectile motion, and then I went and then I did work energy from point A to point D, and I was able to find a spring compression, but I wasn't sure how to check if it cleared the top or not.
Okay. Well, what principle would you use for that?
Work energy, I think.
Yep. So what type of energy is it initially?
Initially would be spring energy.
Yep. So that would just be potential energy due to the spring. Right. So this would be kind of your, I guess I can put delta here. Sorry. Right. And then at this point, what types of energy might I have?
It would just be potential, right? Because if it makes it over the top just barely, then could we assume that velocity is close to 0, or?
That would be the minimum, but it could still have some sort of 1/2 mv squared, right?
Okay.
So, I mean, the big thing would be to see if that, if this ends up being negative, then it doesn't clear it.
Okay.
You follow what I'm saying there?
Yeah.
Okay. And then you also have to worry about what else?
The friction from B to C.
So I'd also have to end up adding in, and how do I include that?
That would go on the left side of the equation.
Okay, and what would it be?
That would be the integral from 0 to rho of mu k mg dx.
I'm sorry, did that. That should be a little, sorry. Mu k mg dx, right?
Yeah.
And then what else do I need to include?
I'm not sure. Oh, that it's negative. Okay.
Okay.
Yeah.
Okay, does that make sense then?
Yeah, it makes sense. I was just confused because I wasn't sure how to check it because I did it and it was all in terms of variables, so I wasn't really sure.
Right. Well, so now you can actually plug in different variables, right? So
You just arbitrary variables.
Yeah, and you guys
Okay.
should be. You know, when I set up new problems, or if I'm working out things for labs or whatever, I actually do them all in variables, and then I put it in a MATLAB program, and basically play around with the numbers. Right. That's kind of how you tend to design things. It's unfortunately
Okay.
not what we do so well in our dynamics class.
Yeah.
But or in statics for that matter, we ought to probably. It's too bad you don't have better computer tools done earlier. But okay. Good. So we've had. Any more questions about this one?
Is the equation that you just wrote, that's from A to the top of to the highest point, correct?
Correct.
Okay.
What about from A to D?
Yeah, you could actually
Would the
use that
height just
same
be
one.
different? Yeah. Okay.
Yeah, the height would be different. Okay. So we've had Annie and Mike ask a question. I want to kind of go around, let everybody see if they've got questions, and then we'll go cycle around. So Wyatt or Jeff or Abdullah, do you guys have questions?
Yeah, I had one. Oh, go for it.
That's okay. Go ahead.
All right, so I had one about dependent motion. There's a few that I was looking at that it was harder to establish the length equation.
Okay.
Due to they're kind of book problems, so I don't know how you would do that on here.
Did you say
or whatnot?
Did you say book ones?
Yes.
Okay. Yeah, let me see what I can, because I can probably just try to draw it if they're not too bad.
Okay. Yeah, so they're both, all the ones that I'm getting tripped up on are mostly where you don't necessarily have a stationary datum.
Okay.
So one of them was like you had a sliding mass A on the left that just slid up and down a rod that
do you know the
had
number
a
there, Jeff?
What?
Do you know the book number or book problem
Oh,
number?
yeah, it's 11,187.
Okay, give me 1 second. Let me just take a look there, and then I'll try to draw it up. 11,187. Okay, so didn't we, and we kind of did, oh, I see what you're saying now here. Yeah, so this one is, give me a second. So it's got basically, and I'm going to take one or two little shortcuts here. So it's got, let's see, so this will take me a second to draw it, sorry. So then it's got a fixed thing there, and it goes up to here and down, and then goes up to the top.
Which book problem is this? Sorry.
Go ahead, Jeff.
11,187.
Thank you.
Okay, so that's C, this is A. Okay, and then this one went to something B, right?
Correct.
Okay, and then that guy can move, right? So if you look at what it says is that A is starting and it's moving downward with a constant acceleration. So we've got this A going down at 7 inches per second squared, right? And then
Right.
collar B moves upward. Right, so this is going upward with a constant acceleration, and its initial velocity is equal to 8 inches per second. Right, so, and then it's giving something with B. Yeah, so it's going through a bunch of that. Then you're going to end up having to use the constant acceleration equations at the end. But
Right.
yeah, so let me take a look and see what I would want to do there. And sometimes with these, what you end up doing is kind of like a subtraction type of deal, if that makes sense to you.
Right, and I mean the algebra after setting up the problem, I'm not too worried about. It's just from here. I mean, I can see visually the relationships between them. You have 4 tensions going up on C, 2 coming down on A, and 1 on B.
Right.
Right. So I can see that, but I don't necessarily know if I were to draw a diagram of this on a test and putting in my datums, putting in my, the length of C and 2 lengths of A and 1 length of B equals a constant. I don't know how I would draw that up.
Yeah, gotcha. So, and for this one, because it doesn't really ask about forces or mg or anything, you don't have to deal with the tensions. But then it's sort of trying to figure out, okay, what am I going to do with sort of this puzzle, right? So,
Right.
like what I would start out with is, well, what are the ones that are kind of straightforward to do for the length?
Well, initially what I would say is the datums being the fixed points at the top and the bottom.
Okay, so
right.
Mm-hmm. So we could certainly do this one here, right?
Right.
As doing like a sort of a YC to start out with.
Right.
Is that okay?
Yep.
And then we could do like a YA to go up to here. And that one's not too bad, right?
No.
Okay, and then I could do the similar for the YB, and then you decide if you want to go from the top or the bottom. Right, so do you have so I might go from just this point right here to do like a YB. Okay, and the reason that's going to kind of help me a little bit, because now I have to add up some of these different distances. Okay, so then if I'm doing my L equation, right, then how much is this?
That's YA.
Okay, and then how much in the end is this going to be?
YA minus whatever the height of C is.
Yeah, or could we use the Y, YC? So maybe in the end, actually, so now, like I just started that, and now I'm thinking, maybe do I want to change that, right? Because I might end up saying it's going to be better to go, right? So, I have to sit and kind of think about what's going to work too, right? So if I do this one instead, right, then what is that length?
So then the first one changes to YC minus YA.
Mm-hmm.
Oh, no.
Well, I would do
How would you express the first one? Oh, a height.
Yeah. So I would do which is constant, minus a YA. Does that make sense to you?
Yeah.
Did I do that okay?
And then, and then plus YC minus YA.
Uh-huh.
And then you got 2 YCs in there.
Yeah.
And then plus a YC minus YB.
Yeah. Okay, so and then plus if we have kind of any little constants. Okay, so we did that a little fast. So let me go back over this, right? So the first one is basically this, you have to just figure out a way to do these in terms of what heights and things you have, right? So this would be for 1, because I've now set, well, this is going to be my H my total height between these things I've established as just an h, right? So that's my overall height between the floor and the ceiling. And then I have to, kind of then it's just like I was saying, sort of a puzzle. So, well, what is that part going to be? Well, that's just going to be whatever YC is, right? That distance there minus whatever that height is, right? Which is really kind of, this part here is a constant between those two, right? So that's my number 2, which is right there. And then my number 3 is going to be these two guys here and here. And then my number 4 is this distance right there, which is going to be that area right there. Okay. So that's a pretty complex constrained motion type of one, right? And it's also got multiple, it's got 2 degrees of freedom. So I'd have to give you information for A and B or A and C for you to be able to solve it out. Okay. So I'd say this one is on the upper level of difficulty for this type of problem.
Right, but for this type of problem, you definitely want us labeling what we're calling YA and stuff and making sure that we can figure out that puzzle on a diagram, correct?
Yeah, because otherwise I don't have, if you want partial credit, then I don't have any other, any other way to really try to judge if you know what you're doing there.
Okay.
Yeah.
So I'm a little confused on the one that you have labeled as 2, just because, so YC doesn't go all the way from the top. So how is that YC minus YA?
Just because this little distance here is always kind of a constant, right, between those two.
Okay, that makes sense.
Yeah. Okay.
Just a quick question. Why couldn't we do like I don't really know how to show you this here, but like so where B is right there, like why can't we set the loop to be a constant? So just have like where 1 is, have that be YA, and then the 4 is tensions, it could be like 4 YC, and then just have another constant, where that middle top loop is.
Yeah, I can't visualize what you're asking. So
Okay.
you might be able to, can you draw on here or not?
Can I? I don't know. Well, okay, let me try and explain this better. So,
we'll see if you can draw it.
Okay.
Yeah, if you go to view options and annotate, we can draw on it.
But I need to do that. Or do you have to do it, or do I?
I think we can. Yeah.
Okay. So I was saying. Okay, so like this area right
Can
here.
everybody else mute theirs for a second? I'm getting a lot of background noise. Please.
Okay, so I'm gonna do this in a different color. So this right here, like set that everything up top, like over that as a constant.
Okay.
And then have this be like Y A, and then so like everything within here be Y 4YC, and then we just have the extra constant. Or would that not work?
Would that work? I'm not sure. I have to think about that for a second, because it may. Because there's multiple ways to go about those. Let me see, because you have YC. I mean, because if you look here, you end up having 4 YCs, right? You have a YC here and 2 there and 1 there. So the question is, do you end up with the other type of terms as well? So maybe I'd have to look at it a little bit more to figure that part out. But and you're going to have YA just go up, you said. Yeah, that might work too, Abdullah.
Okay, for sure.
Okay.
Thanks.
Okay, Wyatt, you had one, right?
Oh. Yeah, I just wanted to double check and make sure that on that last pinball problem, you would have to write the spring coefficient as a function of all the other variables, right?
Yeah, because I think I was asking to solve for the spring coefficient.
Yeah.
Yeah.
Okay, yeah, that's about it.
Okay.
Professor, on these dependent motion problems, can you explain more about how you choose your sign convention?
Yeah, I mean, so the big one there is to see how things are changing, right? So you want to make it go from when you do these, it's got to go from some sort of a fixed point, right? So you need to either reference it from the top or from the bottom, right? And then once you do the L, I mean, your sign convention just works out for you, right? So and that's why you do the whole L deal.
Okay. In one of the examples you did, you went through and you found you derived the velocities and accelerations, and then you said because of your free body diagram, the way you had drawn the axes, that you actually changed the signs.
Yeah, so that was from the quiz.
Right.
Okay, so if you remember how those went, we talked about that in class as well. So let me show you. So basically on those, what I want you to do is recognize what it is you're doing with those things, right? So if you've got, I think in this one it was, right, it kind of went like, I don't remember if this was the exact one. I think it.
Yeah.
Okay. Yeah, so in here, right, and if you just go straight by the, so in here, what you need to do when you're setting up your L1, right, is typically we would do like this for an SA, right, because that's a fixed point, and then we go down here for the SB, right? So when we did all that, we ended up saying, well, it's really SA plus 3SB is going to equal what my length is, okay, plus the constants. And then I end up with, right, where it's 0, and if I take two derivatives, I get this, right, which then says that AAB is equal to minus 3, A of A is equal to minus 3A of B. And all that's saying is that if this accelerates this way more, if that SA is getting bigger, then this SB is getting smaller, right? That's really what that negative sign is meaning.
Right.
Is that okay? So
yeah, that makes sense.
If that's how you set up your free body diagram, then you're fine, right? So if I set up, actually, let me do this way. If I had set up my free body diagram where I said, well, acceleration of A is equal to this, MA is going that way, that's my T, and then I've got N and MG, right? If I set my free body diagram up like that, and I set my free body diagram here like this, and my kinetic diagram, right, where I have 3 T's essentially, and I said, okay, this is going to be going down, right? So if I set that up then and do my math, then this is exactly the same setup, right?
Okay.
But most people ended up not doing this. Most people, including me, right? And I kind of did it that way because I thought that's how most people would do it, right? Because it just kind of makes sense. Now this positive sign really doesn't come into play, right? Because you did this negative sign based on this sign convention.
Okay, gotcha.
Right? Which is opposite of this sign convention.
Right. Okay.
So if you use this one, you're fine. If you use this one, then you don't have a minus sign.
Okay.
So
sorry.
Where I'm a little confused on this is we derived that equation based on the length. Mm-hmm. So how do we, so did we assume that the top box on the platform moved to the left? Is that how we did that?
Yeah, that's what this means up here, right? Because I've set my kind of datum here and going positive to the left, right? So as SA gets bigger, that means the box would move to the left, like what you just said.
Okay.
Okay, so and it should make sense to you that if box A moves to the left, what is box B going to do?
It's gonna move up.
It's going to move upward. Okay,
Mm-hmm.
and at a rate 3 times faster. Right.
Okay.
Okay, so who hadn't had a chance yet? One of the Jeffs maybe, or Abdullah? Do you have a question about any of the problems?
No, not really. I was just kind of tuning in.
Okay. You're a lurker.
Did you want to ask about this one? Did you want to ask about this one? I have a question if nobody else does.
Okay. Did either the Jeffs who hadn't asked one yet have one?
I actually just asked one, so I'm good.
Okay. Go ahead, Annie.
Okay. So I was looking at the PowerPoint where you put up extra examples, and there was one that mentioned a device that like kicks a soccer ball. Do you know which one I'm talking about?
I think so.
It's got like springs on it and a block, and that one exactly. I was wondering, I got really lost on the, like I know like parts of it that go into it, like the spring constant and like impulse, momentum, and impact and stuff, but I'm really lost on like how to do this problem.
Okay, well, I mean, I think you just said how to do it, didn't you? So I guess I need more of a question, more.
I guess I don't know with which part to start with.
Okay, so what? I mean, in here, if you look, you want it to go 30 meters, right?
Yeah.
So that's kind of the end goal. So what's going to make it go 30 meters? How could you figure out just that part?
Would you have to do? I'm trying to think. Would that be part of? It wouldn't be impulse momentum, would it?
Well, what's happening during that rolling of 30 meters?
Well, there's gonna be there was impact, and then there's rolling friction.
Yeah. So during that 30 meters, what's the only thing that's kind of slowing it down?
Friction.
Okay. So then we've got 30 meters, right? And what do I need to know at the very beginning?
The velocity that will get it that way.
Yeah. So this, and whatever you want to call that, let's call it like, I don't know, V3. Okay. So could you solve for that?
Yeah.
Yeah. Right. That's just like, what is this almost exactly like?
I'm not sure.
Right. So I'm trying to get you guys to see how some of these problems are all semi-similar. What is this?
Is it F equals MA?
You could use certainly F equals MA to go through, but I was even meaning what are some problems we've been working a lot recently that's kind of similar to this? You got friction, you got a speed after an impact. What is this really? Anyone? Work energy, and does it remind you of any big thing we've been working on lately?
Yeah,
it's the car.
It's the project, right? It's no different than cars sliding with a friction coefficient of 0.8, right? Than the rolling friction of 0.1.
Okay.
Do you follow me there?
Yeah.
Right. So we're working backwards, exactly like the car project.
Okay.
Okay. Then how do we figure out what this V3 is?
You would have to do. Well, you're given E. So you would work backwards with E to find the velocities that you don't know.
Yep, you're gonna have to do impulse momentum there, right? So you've got the ball hitting this thing, right? And you've got the E, just like you told me. So you're gonna another set of equations, right? So you're gonna have an E relationship, and then you're gonna have the impulse momentum, right? You're gonna have impulse momentum relationships. Is that okay?
Yeah.
So you know the like this V3 after the impact of this one, right? And then in these E and the impulse momentum, you're going to end up having a couple more that you don't know. You know what I mean? So you're going to have this incoming. You know what the incoming ball part is, right? So you know what that is.
Okay.
right? And then from the impulse momentum, you're going to have like an MA VA, right, plus MB VB, where that's the ball. You know what the incoming of the ball is. Then you
Would
know.
the A be the foot technically? Okay.
Yeah, so you can call that whatever you want. Maybe it'd been better to call it like MF, like what you what you said.
Yeah.
Right? So, and then afterwards you can do like an MA VA prime, so that's after the impact, and then you have an MB VB prime, right? And these are all in the normal direction, right? So we're doing these in the normal direction, right? And then we found VB prime. What is VB prime?
We found that was V3.
Yeah, so that's this one, right? I know what the VB initial is because that's the 2 meters. I know what that is. That's 2 meters times a cosine of theta, right? And then my E equation now, I have 2 unknowns in there, right? And again, remember, these are all in the normal direction. So I have this unknown. From the E equation, I have 2 unknowns in that as well. So now I have 2 equations, 2 unknowns. Is that okay?
Yeah.
And then once I have that, right, then it's just a matter of here's my springs here and here. It's a work energy to figure out, well, what is the V of A? Or since I know the V of A right before it, right, then I'm just going to use work and energy with V of A to figure out what the spring coefficient's going to be.
Okay.
Professor?
Yeah.
The V3, once we find VB prime in the normal, that's just the component, and we have to do Pythagorean theorem to get the actual value of V3 to plug into work energy, right?
Correct. You're going to have components that you're going to have to worry about with the VT, right? Because you know what the VT is already.
Right.
Right, because it's going to be just the 2, right? It's going to be the 2, and you know the angle here, so it's going to be 2 times sine of 30.
Right.
So yeah, so this is a complex problem.
Okay.
I did put it on a test one time, and I decided it was a little bit too hard.
On problem 5 of the sheet that you gave us.
Okay, I need a little more. Just can you tell me the description of it?
Yeah, sorry. It was like an arm with a slot in it, and it had a collar that slid in the slot.
Hold on, let's see what I got. That one?
Yeah, that's the one.
Okay.
I was just kind of confused on it. Said that it's in the horizontal plane.
Mm-hmm.
I was having trouble visualizing that.
Yeah, so just pretend like it's on, like, I don't know, maybe the wall. This is the wall right here.
Okay.
Right, so, and it's just acting on a table. So when it says horizontal plane, what's the biggest thing that ends up meaning?
It just means we don't have an mg force?
Correct.
Okay, so if we just see horizontal plane, just think no mg?
Yes.
Okay. All right, that was easy. Thank you.
Yeah, sure. And those are just some of those keywords, right, that you want to look for on problems to see. You know, like we talked a little bit about smooth and rough and horizontal plane, vertical plane. Yeah.
So is that something we'd be able to ask you during an exam?
Yeah, there's going to be some times when I'll look and I'll decide, you know, that's pretty clear. So I might just say, I'll either say, oops, that's something I left off and I shouldn't have, or I might say, well, you know, pretty much everything you need is right there.
Okay.
Yeah. So, but certainly ask.
Okay. Thank you.
Sure.
Sorry, could you explain how there's no weight, so like no mg?
Well, you're just not going to have to worry about the mg here, right? Because it's acting in and out of the page. So it's just going to be like, this is in some sort of slot, right? So what that means is if you draw your FBD right here, then you're not going to draw an mg, right? You don't do that because it's in the horizontal plane and the mg's acting downward into the page, and the normal force from whatever's holding that thing up is acting upward. So it just ends up that in this case, for something like this, N is equal to mg. right? Whereas if it was in the vertical plane, that would not be the case.
So this is basically a top view then, correct?
Exactly right. Yeah, that's a great way to put it. Yes, top view. Okay, more questions?
Yeah, so essentially for this problem, we're looking at it in the R theta, correct?
Yeah, and so why did you decide to do that?
Because it's given in terms of R and omega and radians per second squared and all that. Right.
Yeah,
and circular motion.
Yeah, and it's coming in, right? So that's the big thing, is that the R is changing.
Right. But if we had a problem like this, like if this exact same problem was said that it was in the vertical plane, then you're working more in a still R theta, RY. I mean,
no, you'd still do R theta. It's just now you'd have this type of an mg term that just has you're gonna have to break it into components, right? And you're gonna have a certain component in your sum of forces in R, and you're gonna have a certain component in your transverse direction as well.
Gotcha.
When I was solving for the tension in this problem, I ended up getting so I did sum of the forces in the R direction and got T is equal to M times R times theta dot squared. And M is given in pounds, R is given in inches, but theta dot is given in radians per second. So I was wondering, because radians is technically an SI unit, so would we have to convert that to degrees?
Radians is not an SI unit. Radians is actually unitless. It's a radian is really the ratio of the radius of a circle to its circumference. So radians is actually a unitless one. So we could end up just saying, hey, omega is really equal to 6 nothing, per second.
Oh, okay.
Essentially, right? So, but degrees is just something that, like Carpenter's made up because it's so nice that it's divisible by 4 and by 9 and by, it makes it easy to split up. And actually, I'm not sure about the 12 inches is for sure about that. I'd have to go back and look at that. Does anybody know the history of degrees? It could have some sort of astronomical thing too. I don't know.
Yeah, I'm not really sure. So you wouldn't have to convert any of that. You could just do like theta dot squared, where in this case theta dot would be 6.
You do have to convert the inches
inches to feet.
Right. And you do have to convert the pounds, right?
To
what?
I'm trying to think.
Pounds mass.
No, we don't have pounds, mass, and mechanics. That's thermofluid stuff. So remember weight. Just slugs, yeah. So remember M is equal to weight over G. So you're going to do now for mass, it's going to be 3 over 32.2.
Okay. Thank you.
So whenever I deal with a kinetics problem that is in English units, I just automatically put everything just right away into feet. And then I try to remember to do the 32.2.
And that would come out to pound force, right?
Well, the 3 is pound force, right, is a weight. So we measure here in the US, we measure things in pound force. So we never do anything in pound mass in mechanics in CE204, CE207. That's something that the thermofluids folks kind of put in to make their units work out.
Okay. So
this is our unit of mass. This is what we do for mass. Just take the pounds and divide it by 32.2.
I meant for the tension force.
Yep, tension's always going to be pounds force.
Okay.
Right. And so we pretty much, when you say pounds, that's generally insinuating it's pounds force, right? Like I say, I bet you ask any of your CLA friends if they've heard of Pound's mass, and they probably have not.
Okay.
Right? I mean, because it's just nobody does it except for thermofluids folks.
Yeah.
Okay, more questions.
In that problem that was also on the sheet that you handed out, it was about the machine with the blade that was machining a material. When in the problem statement, it said that the material put a force back on the machine.
Yes.
How are we supposed to know which direction that's in?
Give me a sec. So if you're, hold on for a second. I thought I put it in here, but maybe I didn't.
I think it was in your other one.
Yeah, I tried to add a bunch of these, but I can't remember if I add. Nope, I guess I didn't. Yeah, so I did do the kind of the solution to that one on there as I talked through it. But essentially, what's happening is you've got, you had a hydraulic actuator here, right? And that thing was pushing it over, and now the blade was going this way, and it's cutting through a material, right? And then there was a return energy spring or something here, right?
Yeah.
So that's a really poor drawing of the thing, but you get the idea, right? So that's why my sister's the artist. So as this thing is it's moving that way, cutting through the material. Does that make the right sense to you? So it should make sense to you that you're going to lose energy to that, first of all, that this thing's going this way, and that the cutting, the blade, since it's moving through the material is going to resist that blade motion. Okay, so then that's why you would have the resistant one, where the force is going back that way while the blade pushes that way.
Gotcha. Okay.
All right.
Cool. Thank you.
Sure. More questions?
Originally, when I read this problem, because I think it was an example problem in class, I thought there was like a downward force of 1,700 and then an upward force. Is that something we could ask like during the test, just for clarification?
Sure.
Okay. Just making sure.
Mm-hmm. And some of these, there's probably a dozen different dynamics books out there. So some of these I just pull from other books. So
yeah, there was sorry, go ahead.
Okay. In class, if I remember correctly, you solved this as a work energy problem. I was wondering if you could also use the difference in the force to solve it as like just a force equals ma.
So, all of these you can try to do. So, not like, the easiest answer to that for some of those, like with the work energy, right, that we did in the car crash stuff, right? So it's very straightforward there, because that was, since it's sum of forces equals ma, that was really straightforward to figure out the acceleration and then use kinematics, right? Because that part's pretty straightforward. The problem when you get to those, if you try to do it something like this, is that this spring force now, you've got a component of it acting this way, right? And you'd have to integrate that component of it. So you're going to have some sort of like kx times cosine theta, right? And then you're going to have to do a dx of that throughout this 0.1. I think that was like it moved to the right 0.1 meters or something, right? So then you've got to get a theta. You have to now get theta as a function of x, right? Which you can do with trig, and then you're going to have to do the dx, and by then you're out of time on the test. Right, so it really is going to be a much better approach to do the work energy method here, right? But remember, again, all of this stuff derived from F equals ma, so you can always use that, but the integrals just get so painful that it's much easier, almost always, to do work and energy for a problem like this.
I got you.
Are a lot of these examples or extra problems that you suggested, are they in the book?
Some of them are, yeah, but not all of them.
Okay.
And I wouldn't spend huge amounts of time on trying to to do the full workout part. I mean, you've got, like I was saying before, you've got tons of different examples that show how to work out the full, the full algebraic solutions of these things. Where people typically end up losing the majority of points is just not knowing how to approach one, or really approaching something in the wrong way.
Right.
So.
I have one last question, if that's okay.
Uh-huh.
This was a question. It was 2 sliders in between. Like they couldn't move in the Y direction, and then block B was connected with a spring on the top and bottom. I think it's in this PowerPoint.
Okay, let me look through. Oh, yep. Okay, let me see here. Oops, hold on. Page up. This one?
Yeah. So what I ended up doing, I didn't actually use impulse momentum. Yeah, scratch that. I did, but I didn't use work energy. Is that okay? Basically, what I did was I set up my impulse momentum equation, and then I used my E equation and solved for one of the unknown variables and plugged it in. Is that how you would do this problem?
Well, so B's what's gonna happen after A hits B? What's B gonna do?
It's gonna move a meter to the right, and then you're gonna have stretch in both strings.
Okay, so then, right, how did you account for the springs?
See, that's where I wasn't really sure of, because when I tried to do my work energy, my velocity at the beginning and the velocity at that point where it has moved 1 meter are both 0. So I got kx squared is equal to kx squared, and I wasn't really sure what to do.
Well, I didn't say that the velocity was 0 after it moved a meter to the right.
Oh, okay. Okay. I see. Okay, so then you would do, you would set up the work energy equation with the right half being 1/2 kx squared plus 1/2 mv squared.
Yeah. So, and you've got, I think it's even stretched originally, right? Because it's
it is
stretch length. So yeah, you know how I like to do it, right? So I just do, like, if I said this was T2 plus VG2 plus VE2 plus our U1, that would be 2 to 3 prime, is equal to T3 plus VG3 plus VE3, right? And the VG is 0 because I don't have a slope.
Uh-huh.
Did I have any friction here? I don't think so. Right. So
T2 would be 0, right?
Well, when you analyze in this part, what is the T2 I'm going to use?
Is it right after impact?
Yeah.
Okay.
So T2 I have to find using impulse momentum and my E equation, right?
Okay.
So because remember, I use impulse momentum directly, like immediately before and immediately after the impact.
Okay.
Just like in the car crash, right? So this is why I do the car crash project, because I'm hoping that everybody starts to see the utility of that and how it goes, right? Yeah. And that how so many of these can be worked with the similar principles. VE2 is because it is stretched out a little bit to begin with, right?
Uh-huh.
Then T3 is what I don't know. That's what I'm trying to find, right? I'm trying to find the velocity of block B after it's moved 1 meter, and then this is going to have a value too, right? Because that's going to be my new stretched out direction.
Stretch value.
Yeah.
Okay.
And that's, since I know that that's a 1 meter, right? Then I have a nice little triangle there that I can work through to get the stretch length.
Okay. Okay.
So is for like when we're setting up the VE, like the elastic potential energy, do we just multiply that by 2? So is it like 2 VE?
Yeah.
Okay.
Exactly, since there's 2 springs.
Cool.
Okay. Any other last minute questions?
Is there a solution to this anywhere?
I don't know where I have that, but again, it's kind of like where, I mean, I'm sure I have it somewhere in my files. I need to get back. I've done this, taught this so many times now.
Yeah.
That it is in a file somewhere, and I should grab all that was sort of my goal for the summer, and then I ended up traveling to Peru instead.
Fair enough.
But I think if you can get these, kind of like what I was saying is I want you to think more about what is that process, and then you can get, I think you can solve through things. And, the other thing is sometimes I vary stuff, like I might change the mass or I might make them stick together. And then sometimes I've given people the solutions and they're the wrong one. They're the wrong ones. So somebody else had a question too, I thought.
I think I answered it.
Okay, so study hard. I'm going to sign off so that I can make this. I did record it, but it takes, it's got to process through the whole Zoom video, and then I've got to upload it to YouTube, so it takes a good 30-some minutes for it to process through. Okay, but then I'll post it on Polylearn.
Okay.
All right.
Thank you.
All right, good luck tomorrow, guys.
Yep, bye-bye.
Thank you.
Sure.
Thank you.
Good.